Okay. So how was the exam? Good. Bad. Well, I believe that it wasn't that bad. But any opinion? 어떻게 시험이 어땠어요? 중간 기말이 이것보다 좀 더 쉽게 할까요? 이 정도로 할까요? 조금 더 어떨까요? 비슷하게? Okay, so today we'll be talking about well, if I am about to choose the important number in this course, then I will probably choose the number called determinant. So what is a determinant? So okay, so I'm going to give you the definition first. Okay, so this is a determinant. So in this chapter, so we will be mainly interested in the square matrix. So if I do not mention any further, then you will automatically consider that every matrix in this chapter is a square matrix. So M and the n by n is a space of n by n square matrices over real numbers, or maybe or you can choose to be complex numbers for simple. But however, for simplicity, we will be only interested in we will be discussing the matrices over real numbers. And now we choose a random matrix from this space, and a matrix is then this matrix can be considered as a n tuple of n-dimensional vectors in Rn. So what does it mean? So any typical n by n matrix consists of n low vectors, and each of these low vectors, they are n-dimensional low vectors. So they were put in this order from V1 to Vn. But well, from time to time, I will write this guy as V1, V2, up to Vn. So we will consider a n by n matrix as a n tuple of n-dimensional low vectors. So this is what I mean. So and we are about to compute the number so-called the determinant of matrix A. So this is a number, real number, and this real number is satisfying these three properties. So the first property is multilinear. So what do I mean by multilinear? So the determinant, if you consider A as the n tuple of n-dimensional matrices, so n-dimensional low vectors, then that means for this function determinant, it has n slots from V1 to Vn. So first slot is for the first low vector, and the second slot is for the second low vector, and so on. And the multilinear, I mean by every slot, the function is linear. So, well, it preserves the vector addition and it preserves the scalar multiplication, just like this. So this property I will call the multilinear. And the number two, so this function, determinant of A, must be alternating. So what is alternating? Suppose I have, well, so say that I swap the order of these two low vectors. So, well, you have to be very careful. So this is and this is I's position and this is J's position. But what if I swap these two? Now, in the I's position, I have Vj, and in the J's position, I have Vi. If I swap the order of these two vectors, then I have one negative signs over here. So And this property I will call the alternating property. And finally, the last property is the unitary property. So what is unitary? So you know what I mean by the standard unit vectors. And so determinant of E1, E2, all the way up to En. So in other words, this last property implies that determinant of the identity matrix. So you should be able to understand that this is nothing but the identity matrix, right? Because the first law is E1 and the second law is E2, and if your last law vector is En, then that probably implies that this matrix must be the identity. So the last property can be translated as the determinant of the identity matrix is precisely 1. Okay. So, and any function satisfying these three properties, any function satisfying these three properties, we will call this function is a determinant. And sometimes I'm going to say this is determinant of A. Okay. All right. And today we'll be talking about very important properties of the determinant. And I will begin from the easiest one. And if there is two different indices, ij from 1 to n, and they are different. So I is different from j, and vi is the vj. So, so that means if your matrix, in other words, conclusion first, then determinant of this matrix must be 0. So in other words, the determinant of, well, suppose that you have a matrix that has two same row vectors. Then the determinant of that matrix must be 0. Okay. So if you have two identical rows on your square matrix, then determinant of that matrix must be 0. So why? You can easily see this just by looking the property number 2 over here, alternating. So if the alternating property means that if you swap these two row vectors, then you have to change the sign. So vi well, and by alternating property, so this is the i's position and this is j's position. But swapping these two row vectors, I have one negative sign. But also we are assuming that vi is the same as vj. So this negative sign just carries over. But since vi was the same as vj and vj was the same as vi, so this is this. So and now we know that this is precisely the same as this one, but the sign changes. So this implies 2 times of determinant has to be 0. And the only possible explanation is the determinant of this matrix must be 0. Also, likewise, if your matrix A has a 0 row, then determinant of A must be 0. Okay. Okay. All right. Okay. Okay. And so by now, some of you might be wondering. So can you specify one exact function which satisfies all these three properties? And it turns out there is only one function satisfying these three properties at the same time. So well, at least when your matrix is 2 by 2 matrix, then there is only one such a function. Well, I have a 2 by 2 matrix, and I want to compute the determinant of this number using these three properties that I listed above. And well, it turns out the determinant of this 2 by 2 matrix is this guy times this minus this guy times that. Okay, so okay, let me justify this step by step. I am interested in finding the determinant of this matrix, and you can this matrix has two-dimensional row vectors A, B, and C, D. So please allow me to write in this way. And A, B, this first vector can be also written as A, 0 plus 0, B. And in the second slot, C, D can be written as C, 0 plus 0, D. Okay. Now, I am taking advantage of the multilinear property of the determinant. So this is the first slot is nothing but the sum of two vectors, and this is another sum of two vectors. So if I expand this, then I will get 4 terms by multilinearity. Okay. So this determinant of this guy, this, which is this, and this guy, that, which is this, and this guy, and this, which is the third term, and this guy, and this, which is the last one. Okay. Okay. Now, again, because of the linearity, so well, we can consider this one as A, 0 as A times 1, 0, and C, 0 as C times 1, 0. And again, by multilinearity, this A, C can be put out of this determinant function. So this first term can be written as A times C times determinant of 1, 0 and 1, 0. Okay. And same thing is true for the second term. So I have A and I have D here. So AD goes out of this determinant, and determinant of 1, 0, 0, 1. And determinant of this guy is now B times C, determinant of 0, 1, 1, 0. And finally, this is B times Z times determinant of 0, 1, 0, 1. Okay. Agreed? Okay. And please let me get rid of some trivialities. And I believe this guy must be 0 because it has two same lows here and there. So, and they are different. So, and they are also different. And I have two same lows, 0, 1 and 0, 1. So it goes to 0. Okay. Now what? And I believe this guy must be 0. This guy must be 1. Why? Because this is identity matrix. Okay. And is it 1? No, this is not 1. But this is not identity either. So what can I do for this? Now this is time to use the alternating property of the determinant. This is 1, 0, 1, and 1, 0. But if I swap the order of these two, then this inside thing is going to be the identity. But for the price of changing the sign. Why? Because I have changed the order of two row vectors. So this is not +1 anymore. So this is going to be determinant of identity with negative sign over here. Okay, so this is AD minus BC. So, well, there is a well-defined formula for the determinant of 2 by 2 matrix. Then this formula was obtained just by using these three properties. All right. Okay. And by the way, if there's anyone who have never heard about this formula, yeah, I really hate to say so, but well, you should better memorize this. But which is not that hard, right? So diagonal entries time multiplied minus this anti-diagonal entries multiplied. Okay, so we are learning some few basic properties of the determinant. And the next property is this. The elementary law operation leaves the determinant unchanged. But there is a huge exception, except for row exchange and scalar multiplication. Well, do you remember the elementary law operations? So there are a couple of elementary operations. Well, you are allowed to multiply some law and add it to the another law, which was the first elementary law operation. And also you can freely multiply any law by any non-zero scalar. And also you're free to exchange the order of the laws. So these three things we call the elementary law operations. And well, except for the law exchange and scalar multiplication, well, then so there, which just leaves us one elementary law operations. Adding scalar to one row vector and add it to the another. Sorry, multiply a scalar to one row vector and add it to the another. Leaves the determinant unchanged. All right, so let me check this. This is, say this is my original matrix A. And here I have multiplied, so I apply the elementary operations towards these two laws. In fact, I have multiplied a number alpha to the vector, to the ith law vector and added to the jth law, which is precisely this. Okay. Now I am computing the determinant of this matrix, but I can, well, because of the multilinear property of the matrix, the determinant, so this guy can be split into these two terms of determinant of V1, Vi, Vj, Vn, which is this, plus alpha times V1, Vi, Vi, and Vn, which is this. Okay. But since I can see two same laws on the i's and the j's, so this guy automatically is going to be 0. So which is just determinant of this original matrix, which is determinant of A. Okay, so these elementary law operations doesn't change the value of the determinant. But however, but you have to be careful if you exchange the order of two laws, then determinant definitely changes by the sign. And if you multiply any law by some scalar, suppose that you multiply this law by number 7, then the whole determinant also changes by a factor of 7. Okay. All right. So, okay. All right. I guess this theorem is the most important theorem for today's lecture. And it gave us 4 important properties of the determinant. So let me try to read it one by one. Determinant of a triangular matrix is a product of the diagonal entries. Oh, sorry. As a matter of fact, I mean this is a upper triangular matrix. Sorry. Well, just imagine a square and upper triangular matrix. Then the determinant of that matrix is nothing but the product of the diagonal entries, which is very easy to compute. Okay, number 2. The matrix A is invertible if and only if the determinant is non-zero. So property number 2 is, well, is I guess the most important property of the determinant, because later on you will see the algorithm to compute the determinant of any matrix of any size. Then once you can compute the determinant of the matrix, and if the number equals to 0, determinant equals to 0, then which tells us that the invertibility of the original matrix A. They are actually the if and only conditions. Okay, and number 3. So also this is also very useful. So determinant, suppose that you have the 2 matrices of the same size. They are 2 n by n matrices, A and B. And determinant of A times B is the determinant of A times determinant of B. So determinant is kind of preserving the matrix multiplication, the structure of the multiplication. But this property is not true for the addition. So I mean, determinant of A plus B is not the same as determinant of A plus determinant of B. Those two things, they are completely different. But however, it preserves the multiplicative structure between real numbers and the matrices. Finally, determinant also unchanged under transposition. If you take a transpose of a matrix, then the determinant of the transposed matrix is the same as the original determinant of the original matrix. Okay. So these 4 properties. So I will try to prove one by one. Okay. All right. Number 1 first. Okay. So we are interested in finding the determinant of the upper triangular matrix. Okay, so we are going to consider 2 cases. Suppose that the diagonals of the upper triangular matrix is non-zero. So we are going to consider this case first. So if the diagonals of the upper triangular matrix are all non-zero, that means it's a full base, so full pivot matrix. And in case your matrix is full pivot diagonal matrix, upper triangular matrix, then again, by using the elementary law operations, you can change that matrix into a diagonal matrix, right? Then the matrix can be transformed to a diagonal matrix by using elementary law operations. So without exchanging the law of orders, and without multiplying any scalar to any laws. Then, so therefore, the determinant of this original upper triangular matrix must be the same as the determinant of this diagonal matrix, right? So we are interested in finding the determinant of the diagonal matrix, A11, A22. So this lower diagonal is 0, and I have some random numbers on the upper diagonal, but by elementary law operations, this determinant is the same as that determinant. Now, so what do you think is the determinant of this diagonal matrix? At this point, I need to use the multilinear property of the determinant. Well, I can think of this guy as 1 times A11. This is 1 times A22, and 1 times ANN. And since the determinant is multilinear, so A11, A22, ANN, and determinant of, so 1, 1, 1. Okay. Now, finally, the determinant must be unitary. So this number must be 1. Okay. Therefore, in this case, the determinant of this upper triangular matrix is just a product of the diagonal entries. Okay. Okay. Now, what if the diagonal has at least 1 0 numbers? So in that case, any of is diagonals is 0, then again, by using elementary law operations, we can turn the matrix into an echelon form. Okay. And in this case, my diagonal contains at least 1 0 entry. Then what do you think is the echelon form of that matrix? Then the echelon form must contain at least 1 0 rows, right? And if your matrix contains 1, 0 rows, then because of this corollary, then determinant of that matrix must be 0, right? So the the echelon matrix has a 0 row, so its determinant is 0. Okay. Therefore, so I can still, therefore, even in this case, I can still say the determinant of this matrix is the same as the product of the diagonal entries. Okay. They are all 0. So determinant of A is, which is 0, and which is just 1, 2, 2. Okay, great. So property number 1 is done. So, before I try to prove the statement number 2, this proof gives us the idea how to compute the determinant of any square matrix. Well, just try to convert your n by n square matrix into upper triangular matrix by using Gaussian elimination. Okay, if you can choose, if you can turn your matrix into the upper triangular matrix without any row exchange, then that is good. Then if you can do that, then try just multiply all those diagonal entries of the upper triangular matrix. Then that number is going to be the determinant of your matrix. And if you cannot make it into the upper triangular matrix without using row exchange, then you can still do the row exchange. But in that case, you have to remember, whenever you apply at one row exchange, then the sign of the determinant changes by sign. Okay. So don't forget to keep track of the sign. So once you can do that, you can still compute the determinant of the matrix, even if you apply the row exchanges. All right. And number 2. So what was statement number 2? Matrix is invertible if and only if determinant is non-zero. Okay. So this is easy. So determinant of A, which is the plus or minus determinant of is echelon matrix U. Okay. The sign must be plus if the number of row exchange was even, and the sign here should be negative if your number of row exchange is odd. Okay. Anyway, so determinant of A is plus minus of determinant of U, and this is because of the statement number 1. This is the product of all those diagonals. And also you have to remember, the matrix A is singular if and only if your matrix is full pivot matrix, which implies that so A is non-singular if and only if your matrix is a full pivot matrix. So in other words, A is singular matrix if and only if any of its diagonal matrix of U equals to 0. Okay. And diagonals of U equals to 0 implies determinant of A equals to 0. Okay? Diagonals of U equals to 0 if and only if the product of all diagonal is non-zero. Product of all diagonal equals to 0. Which is if and only if the determinant of A is 0. Okay? So they are all related. And what now? The number 3. For any n by n matrices, the determinant of A times B is determinant of A times determinant of B. So, well, as a matter of fact, to prove the statement number 3 requires a lot of time and effort. But, so this is actually my favorite part of this Gilbert Strength textbook. So he gives us very elegant proof of the statement number 3. So let me try to follow his idea one by one. Number 3. Sorry. So we are about to prove that A times B is determinant of A times determinant of B. So this is what we are supposed to prove. And we consider 2 cases. Suppose that B is a non-singular matrix. In other words, B is invertible matrix. So determinant of B is non-zero. Then we consider a function, so which I will name MD, which is a function from space of all n by n matrices to real numbers defined by I'm going to define my function D just like this. For just choose any matrix, I will say A, and D of A was in order to compute this number, then first we compute the determinant of A times B. We compute that number and divide everything by determinant of B, which is quite doable because the determinant of B is assumed to be non-zero. Okay. Okay. Now, what I'm going to prove is very simple. I will claim this newly defined function D is satisfying multilinear and alternating and unitary. If I can show my newly defined function D is satisfying all these 3 properties, then maybe I am safe to say this function D is in fact the determinant. Okay. All right. So the proof goes like this. First, I will prove that D is a multilinear function. So I will compute this matrix. So V1 Vn, but here I have A times B plus B times W. And because of this definition, I am supposed to compute the determinant of this matrix. This is my matrix A times matrix B and divide everything by determinant of B. Okay. But so I have this is n by n matrix times another n by n matrix. But I can still consider every row of this resulting matrix as this row times that. This is 1 by n times n by n. So which is n by n as 1 by n, sorry. So this first row of the resulting matrix can be understood as V1 times B, and this is V2 times B, and this guy times B, and Vn times B. The resulting matrix must consist of these looking rows. Now, here, now I'm supposed to compute the determinant of this matrix, but we know the determinant is already a multilinear function. So determinant of this guy can be split into these two terms, A times V times B plus B times determinant of V1 WB and Vn. Okay. Now, if I divide sum of these two numbers by determinant of B, then I can say this is A times D of this matrix plus B times D of that matrix. Okay. And just let me focus on the beginning and the end. Then D of this guy, we were able to split this one into A times D of this plus B times D of that. So we are safe to say the function D is multilinear on the ith position. Therefore, every position. Okay. Okay. And now I want to show that D is also alternating function. Oops, sorry. Okay, yeah, all right. So I want to compute this looking matrix from V1, Vi, and Vj, and all the way to the Vn. And again, by definition, so determinant of this matrix and multiply by matrix B, and everything divided by determinant of B. Okay, and by using same logic, product of these two matrices, these two matrices. So I can say this is V1 times B, Vi times B, Vj times B, all the way to Vn times B. And we are supposed to compute the determinant of this matrix. But again, we already know the determinant is alternating function. So therefore, if I swap the order of these two rows, then I need to put the one negative sign over here. Okay, so this is Vi and Vj, but this is Vj and Vi. So these two guys has been swapped and divided by determinant of B, obviously. But this last expression can be written as minus of D of this matrix. V1, Vj, Vi, Vn. V1, Vj, Vi, Vn. Okay. So as a result, if you're just focusing on the first and the last expression, then I am pretty sure that my newly defined function D is also alternating function. Okay. And finally, my function D is unitary. So to show that D is unitary, then I will need to see if I plug in the identity matrix to the function D, then has to be 1. But because of the definition, D of I is determinant of I times B divided by determinant of B, But you know, I times some any matrix is the I times B is B. So therefore, just determinant of B that divided by determinant of B, which is 1. So D is unitary. Great. So, okay. So we have defined function like this, but it turns out this function is actually a determinant. Therefore, determinant of A, which was defined to be determinant of A times B divided by determinant of B. But it turned out this is nothing but determinant of A. Therefore, determinant of A times determinant of B is determinant A times B. Okay. So, so this formula was true if B is a non-singular matrix. Now, question is, what if my matrix B is a singular matrix? So let us also consider that case. What if B is a singular matrix? First, you should be able to see this. The rank of the matrix AB is less than equals to rank of, the minimum of rank of A and rank of B. Oh, wait a minute. We have seen this problem before in our midterm examination. Were you able to solve this? Okay, so yeah, so if you, okay, good. The rank of AB is always less than equals to rank of A, minimum of the rank of A and rank of B. So, so that means if B is a singular matrix, suppose that A and B, they are both n by n matrices. And if B is a singular matrix, then rank of B must be strictly less than n. Right? Therefore, rank of AB also must be strictly less than n. So rank of AB is less than rank of B. So since we are assuming that this guy is not a full rank matrix because we are assuming B is a singular. Therefore, AB, the matrix of AB, the matrix AB also must not be a full rank matrix. Therefore, AB is a singular matrix. Then determinant of AB, which equals to 0, because we know that AB is singular, the matrix is singular if and only if its determinant equals to 0. But this is also the same as determinant of A times determinant of B. So this guy times this must be also equal to 0 because this number has to be 0, right? Because B was assumed to be singular. Okay, so therefore this formula is also true even if your B is singular matrix. So proof is done. Okay. All right. Okay. And what now? So we are done for number 3. And I'm sorry. Oh, so also finally, we need to show that determinant unchanges under transposition. Determinant of A transpose is determinant of A. Also, we need to consider 2 different cases. Case number 1 is also we first consider A is a singular matrix. But this is easy. Suppose that A is singular. But however, we also know that the rank of A is the same as the rank of A transpose. That means if A is singular matrix, then A transpose must be singular too. Therefore, determinant of A must be 0 because of the assumption. And determinant of A transpose also must be 0. Okay. So, so in this case, if A is singular, then this equality is true, obviously. The second case, A is a non-singular matrix. To prove this, okay, we have to consider the A is LU factorization. We consider A is LDU factorization. No, hold on. So sometimes I may need the low permutation. So yeah. So precisely speaking, so I will need to consider PA is LDU factorization. Okay. Okay. So well, I have the LDU factorization of the matrix PA. Then now we apply the function determinant to the both sides of this equation. Then determinant of PA is determinant of LDU. But however, determinant preserving the matrix multiplication. So determinant of P times determinant of A is determinant of L, determinant of D, and determinant of U. So I can break down like this. Okay. And I feel like sorry, this is not my just feeling, but I am pretty sure that the determinant of this matrix must be 1. Why? Because, well, so just remember the LDU factorization. So what is the LDU factorization? When in this LDU factorization, this matrix L is the lower triangular matrix with all whose diagonals are all 1s, right? And the matrix U is the upper triangular matrix whose diagonals are all 1s. And you remember that the determinant of the upper triangular matrix is nothing but the product of its all diagonal matrix. Therefore, and since its diagonals are all 1s, therefore this guy must be 1. Okay. And also, I am pretty sure that determinant of this lower triangular matrix L must be 1. Why? Because these diagonals are all ones, and applying the elementary law operations, we can change it into the low. So echelon matrix of this guy is the identity matrix, right? Therefore, a determinant of this matrix is also going to be 1. So now I can say the determinant of matrix A is determinant of the diagonal matrix divided by determinant of matrix P. Okay. So also you have to see, you should be able to see that P times P transpose is identity. Why is that? Can you see this? Well, so the P is the low exchange matrix. So if you remember the low exchange matrix, then its rows or its columns is actually is the columns of P is just nothing but the shuffle of the columns of the identity matrix. So just take any permutation of the columns of the identity matrix, then that is going to be your matrix P. Okay, so that means every column of matrix P, they are also normal vectors, right? Because their columns are all they came from the identity matrix. And so P is an orthogonal matrix, therefore its inverse must be its transpose. So multiplying these two is going to be identity. Okay. Okay, great. P is an orthogonal matrix. So determinant of P times determinant of P transpose is determinant of identity, but which is 1. Okay. Okay. Then what is determinant of P? So determinant must be the real number. So therefore, oh, okay, right. I got confused a little. Sorry. And I claim the determinant of P must be plus or minus 1. Why? Because so their rows also the rows of the permutation matrix P came from the identity matrix, right? But the order has been changed. So the determinant of the identity matrix is 1, but once you swap the order of two rows, it changes sign. But so therefore, so suppose that you obtain your matrix P by swapping 5 times the identity matrix. Then the sign of this guy, then this guy must be minus 1 to the 5th times 1, right? So this guy must be always plus or minus 1. So therefore, if this guy is plus or minus 1, then this guy must be also plus or minus 1. Okay, so to be precise, if this is minus 1 to the case, minus 1 to the power of k, then this guy also must be the minus 1 to the power of k. I mean, so in other words, the parity of these two numbers must be the same. parity가 뭐예요? sign. 그러니까 sign이 똑같아야 된다. Right? So, the determinant of P is minus 1 to the k's. So, and this is also true for determinant of P transposed. Okay, now good. Yeah. So we apply the determinant function towards this equality. now I'm going to do the same thing, but taking the transpose of both sides of this equation. Let us consider taking transpose, then A transpose, P transpose is U transpose, D transpose, and L transpose. Okay. Then taking the determinant of A transpose, P transpose, and UT, DT, LT. But however, by the same reason, I guess the determinant of this and determinant of that must be 1. And also, so transposition of diagonal matrix is actually nothing, unchanged. So I say this is just simply determinant of D. So determinant of A transpose is determinant of D divided by determinant of P transpose. But we already know the determinant of P and P transpose, they must be the same. So it's just determinant of D minus, divided by determinant of P. And comparing this and that, those two numbers are the same number. Okay. Okay, great. So the biggest theorem has been proved. Great. So am I good to turn to the next page? Yeah, thank you. Okay. And sorry, not yet. I changed my mind, sorry. 4.3. So in this chapter, in this section, I'm going to give you the explicit formula to compute the determinant of matrix of any size, any square matrix. First, we will begin from the determinant of the two. So the easiest case, the determinant of a 1x1 matrix is actually nothing, just the number itself. And determinant of 2x2 matrix that we have already discussed earlier. So determinant of A, B, C, D is AD minus BC. And sometimes we denote, is denoted by A, B, C, D. So if there is a bracket between these numbers, then usually it refers the matrix. But if I draw a vertical line here and there, then you should consider this as a determinant of the matrix. Okay. Okay. Now, so since we already know the formula for the determinant of the 2x2 matrix, so let me try to find out the formula for the determinant of the 3x3 matrix. So let us consider the case when the matrix A belongs to the space of all matrix of 3x3. This is going to be a little bit time consuming. So Oh, sorry. Oops. Okay. So for now, okay, let me try to compute the determinant of this 3 by 3 matrix. And the determinant is multilinear. So I'm going to, and therefore this determinant must be also linear on the first law. Therefore, I can break down this first law as these 3 terms. A, and these two guys, these two laws, they just carries over. And so this plus that. Okay. Because the determinant is multilinear. All right. But so I am supposed to compute the determinant of 3 different matrices. And also the determinant is also multilinear for the second law. So I'm going to apply the multilinearity on the second law of this first term, which is, so this guy and the A11 and the last law, they just carries over. But the second law has been broken down into A21, 22, and 23. Okay. And same thing is true for the second determinant. So because I am using the multilinearity of the second law, so A12 and this last law just carries over, but the second law has been broken down into like this. And likewise, this last term can be broken down just like that. Okay. So therefore, I am about to compute the determinant of all these 9 different 3 by 3 matrices. Okay, but yeah, it looks like things are getting worse and worse, but it's not that complicated. Because, and I am pretty sure that this number must be 0. Can you see why? Because, well, because of multilinearity, I can say this is A11 times A21 times 100, 100, and the last law. And if you do that, then I have 2 same laws on the top and the second, top and the middle. Therefore, this guy must be 0. Okay, automatically. So I don't need to worry about this anymore. This guy goes to 0. And because of same logic, so getting rid of, so this is actually scalar multiple of 1, 0, 1, 0, 0, 1, 0, and the last law. Therefore, this guy also must be 0. And this guy also equals to 0. Okay. All right. So now we only have the 6 terms, the 6 determinant. And also, lastly, the determinant is also multilinear on the last law. So I want to break down this guy into 3 different terms. Just like this. A11, A22, A31. So this single determinant also can be broken down into these 3. Okay. And I'm also sure that this guy must be 0. Why? Because, well, up to scalar multiple. So I can see 2 same laws, top and the bottom, and the middle and bottom. So those 2 guys must be 0. But this guy, it may be non-zero number. So So even though it looks like I have the 3 different determinants from this guy, but I can see only one possibly non-zero determinant out of the first term, which is this. Okay. So I'm using the same logic. So from here, I can derive only one possibly non-zero determinant, which is this, and this, which is this. And so there's one number here, this, so this, and this, which is this, and this, and this survives, which appears here, and this, and this, okay, and this, and this. So I only have 6 different determinants left. Okay. Okay, great. Now I have 6 terms, but because of the multilinearity, so I can say the first term can be transformed into A11 times A22 times A33 times determinant of 1, 1, 1. Okay, which is this. Likewise, this guy can be transformed into all these numbers times 1, 1, 1. These numbers times 1, 1, 1, and so on. Okay. So I have these 6 different terms over here. Okay. Are you good? Any questions so far? Am I too fast? Good. Okay. All right. I believe I'm good. Now it remains to determine all these determinants. Oh, I can easily see the determinant of this guy is 1. Okay. So what is the determinant of this guy? Right, because so I can obtain this matrix from the identity by swapping the order of the second, the middle, and the bottom rows. Okay, so this is -1. This is also -1. I believe this is also -1 because swapping the first and the last obtains this. These 2 things, they are somehow tricky. I can never be achieved these 2 matrices by applying 1 row exchange. So I will need to apply 2 row exchanges to obtain these 2 matrices. Agreed? So therefore, these 2 guys must be not -1, but these 2 guys must be +1. Okay. Okay, therefore, so this guy just carries over, but this is 1. This guy just also carries over, but since we know that we all agree that this is -1, so I have the negative sign here. This guy over here, but this is -1, so this is minus sign here. This is +1, this is +1. So these 2 guys, they carry over with the same signs. And this guy over here and here, -1. So this is the formula for the determinant of the 3x3 matrix. Oh, I already ran out of time. So, and yeah, I really hate to say so, but you should memorize this. Well, because computation of 3x3 matrices appears a lot. Sorry. So this is my rule of thumb. This and this and this. So these 3 numbers and these 3 numbers and these 3 numbers, multiple of these numbers, they appear with the positive sign. And this, this, and this. The product of these three numbers and these three numbers and these three numbers appears with negative signs. So you have total 6 terms. All right, so this is for today, and see you next time.